So I'd like to thank the organizers for giving me this opportunity. I'm Najam Hasan from Maulana Azad National Urdu University, India. I'll be speaking on science cases of machine learning in astronomy. I'll be essentially talking about work done by our students, Mahmood, who's now in Wayne State University, Michigan, Mudassir and Saif, who are with us in Hyderabad, and my collaborator, Priya Hassan. Yeah, so we are living in time when astronomy has changed from data poor to a data-rich science, and uh, this arrow indicates how from 1980s megabytes have gone to gigabytes of data, which is coming into astronomy, to terabytes, petabytes, and exabytes. With these large astronomical surveys, coupled with advances in information technology and computing, it is becoming essential for astronomers to handle the big data sets and interpret the complex astrophysical problems by using sophisticated statistical techniques and technology. Uh, Astronomy has moved from hypothesis driven science to data driven science. We have now large data sets and streams. When on data exploration, we see patterns which lead to hypotheses, theories, and give out lead to conducting new experiments and uh, understanding what's happening around. Both the approaches are complementary to each other. As we collect huge amounts of astronomical data, it has gone beyond human capacity to analyze without help of machines. It has become essential to train computers to sift through the data, identify important patterns, and find connections that might otherwise be missed. This process is, like we all know, is called machine learning, and it's an essential aspect of modern astronomy. From 1950s, from the time artificial intelligence was coined by Turing, where early artificial intelligence stirred excitement, to 1980s, where machine learning begins to flourish, and in 2010 and beyond, the deep learning breakthroughs drive AI to bloom. Needless to say that there are various applications of machine learning in all aspects of human endeavor, from automatic language translations to medical diagnostics to all kinds of uh, areas which touch our concerns. But we would be more interested in aspects of astronomy. So we have machine learning, we have the supervised, unsupervised, and reinforcement learning. And very roughly, the two things is it can be very effectively used for classification and for regression. To find some kind of a relationship for continuous data, that's where the regression comes in. While to be able to classify objects, for example, classifying galaxies, the different morphological types into spiral, ellipticals, or lenticulars, or when if it comes to star clusters, to find out the members and non-members from it, right, and differentiate between objects which are stars, galaxies, or other artifacts. Um, Galaxy Zoo project is an example where we do this classification of galaxies, where we train machines to identify what are spirals, what are lenticulars, and so on. And then it shifts through this large amount of data surveys, which is very difficult for humans to go through it themselves. The machines are pretty efficient in into this. Machine learning has also very effectively been used in variable star classifications by training them to understand the light curves and classifying them into intrinsic and extrinsic groups, or further classifying into pulsating stars, eruptive, cataclysmic, and eclipsing binaries, and further into types of seaweed, RR Lyrae, T. tauri, and so on, where from the light curve itself, we can classify these variables. Also, it has been used in exoplanet discoveries by training machines to look at the light curves and get parameters for the exoplanets. And similarly, from spectra, finding out the redshifts very effectively. Interestingly, even a problem like the three-body problem from celestial mechanics, which is a 400-year-old problem, where if you look at three mass points which are moving under mutual gravitational attraction, in 1800s it was shown that there is no general closed form solution for this, uh, but there are some numerical solutions. These have a lot of applications in various things like planetary systems, understanding the sun, earth, moon system, and so on. And though we do not find solutions, we cannot find general solutions to this problem. Machines have been trained to find a solution to the three-body problem, giving them different initial conditions, and they are much more efficient than the usual numerical techniques which have been used for over 400 years. Uh, Coming to this beautiful image which took all of us by storm, the EHT team developed a computational imaging algorithms using this convolution neural networks and to fill in the blanks of the data and generate this beautiful image of the black hole. I'll come to the special case of star clusters because this is where we have been working for some time. Star clusters are the basic building blocks of galaxies. To understand the formation and evolution of galaxies, it's essential to understand star cluster populations, young associations, open clusters, and globular clusters. And uh, one of the issues of finding important issues of studying star clusters is to find membership of stars. So these stars and clusters are formed at the same time, same distance, they have the same chemical composition, and they vary only in masses. Uh, we have wealth of interesting and good data, high quality astrometric data from Gaia. The satellite sitting at the Lagrangian point 2 in a research orbit is sending us tremendous amount of data, and uh, one needs to look into this to understand star clusters better. So, like I mentioned, when you take a snapshot, very important aspect of this is which of the stars here will actually belong to the cluster, or they just happen to be in that region of the sky which you are seeing. So we have used various techniques, supervised, unsupervised method. We have used the random forest. We have used DBSCAN, HDBSCAN optics, and so on. And we've got some interesting results. This is what I'm going to say the remaining time which I have with me. So in supervised methods, where we need good training data, the pros of it is it can perform better or give good accuracy to predictions even with a high number of data. While the cons are if the training sets are poor or inaccurate, then it can lead to uh, issues and problems. In one of our papers, we looked at membership of stars in open clusters using random forests with Gaia data. We chose 9 open clusters and we took data from Gaia DR2. The list of these clusters are given here: NGC 581, 1893, IC 1805, and so on. We chose this sample because these clusters they range in ages from 1.3 to 20 billion years, and their galactocentric distances range from 7.3 to 14.5 kiloparsecs. And we selected them from different galactic latitudes and longitudes. So we were interested in looking at different sets of star clusters located different in different positions in the galaxy and varying in ages and so on. We used, in this case, it was a supervised uh, technique. So we used the membership data from Canted Gordon, which is also based on Gaia DR2 as the training set. And we use random forest, which is a supervised method. Oh, the plots which you see here of proper motion and parallax plots, the left screen is the pink stars, pinkish reddish stars, which you see are the canted Gordon ones, and the blue ones are the members which we could determine. Canted Gordon have gone down to 18th magnitude, while we chose the cutoff to 20th magnitude. So going to the lower end of the magnitude diagram. So we can see from these plots, these are the plots for all the 9 different clusters which we studied, and we see that we are getting many more stars, uh, much more than what Canted Gordon got, and we could even get uh, the outer regions of the cluster as well. On the right hand side, we have these histograms which are the parallax plotted. So the orange curves are the Canted Gordon ones, the blue ones are the members which we derived, and the green is a combined one. And here are for the same 9 uh, samples where we have the proper motion RA, proper motion deck plots, and on the left hand side, the middle one gives us the RA deck uh, one in the position space, and we have the color magnitude diagrams on the right side. And what we notice is the ones in orange are the Canted Gordon members, the ones in the blue are the additional members which we found. And as you can see, in some of these, we can see substructures in their velocity space as well as in the position space. We can see, for example, in NGC 2264, Canted Gordon sees it only as a single cluster, but we are in the velocity space, we are seeing substructures in that. And so is the case for some other clusters. Further, we can see that we are getting many more pre-sequence stars which are missed out by the Hampton God.
Professor
We did
Hassan,
the
you
valid.
have 2 minutes remaining.
So we did the validation by looking at the um, validated this by Apogee and Gala Soez, and uh, and you can see that the members which we get are members increased by 2 to 3 times. It improved the accuracy in determining the various parameters of star clusters ranging from distance, extinction, mass, functions, and the sizes of the clusters were also revised. Likely cluster members, we could give probability of which is the likely member or not, and which are the escaped members. So, coming to the unsupervised learning techniques, we used um, uh, DBSCAN and the Gaussian mixture modeling, and again we looked at 9 clusters, and what you see here in the red blob is the Canted Gordon one, while the blue ones are the clusters which we found. And we further did validation by looking at the spectroscopic data got from the Apogee and the Gala surveys. And we saw that in these 17 chemical evidences, the upper graph shows Canted Gordons, while the lower one gives us for our members, showing that these members, the additional members which we got, they do belong to the cluster. Further, we use this Azteca, and we got further parameters of these clusters and calculated the distances and the ages very successfully. The sample of stars and clusters can be increased by a large factor of almost 1 to 2 times. This improves accuracy in determining various parameters. The size is studied of the clusters and increase with increasing membership, and can study the outer regions of the cluster. As we did not have photometric data while estimating membership, we can identify variables, pre-main sequence stars, as well as other possible non-main sequence members of these clusters. Further, we use the DBSCAN method algorithm and HDBSCAN, and we could enrich the clusters. We could see that we could get many more objects than traditionally, what we could get traditionally in a very organized techniques. So yeah, so these are some plots of Azteca from M67, and here are the results. For these 9 clusters, we could get the ages. If you see, the age is what Azteca gives is 9.38, while the reported age is 9.63, 7. NGC 224 is 7.3 to 7.1. So most of the ages and the distances are pretty much in agreement with the derived parameters by Kant and Gordon. So we were essentially interested in seeing which algorithm works best, and we realized that when uh, the field stars are much more, then the DB scan works much better. And we further used the techniques. We used optics, HDB scan and DB scan to study the serpent's cloud, which are molecular cloud star-forming regions. And we used available YSO catalogs of X-ray and IR. We found parameters, and using those parameters, fixed up the parameters and downloaded the Gaia data. Used DB scan methods and optics to get objects, and we get 2 to 3 times increase in these.
Yeah,
And
Professor Hassan, sorry to interrupt you, but your time is over now. Could you please wind up your presentation?
yeah, so this is uh, so YSO population 2 we got was much higher. These are the criteria which we use. RUW was less than 1.5, and PMRA lying between 1 and 5. And we got 822 common YSO members in this region, plotted them on the extinction map, and found the YSO classification further by using the 2 mass and the WISE data. So thank you. I'll stop with this.